Hello everyone, welcome to this channel NCERT Physics Simplified, and in this video I'm going to explain you chapter number 4 of NCERT Physics class 12. This is moving charges and magnetism. Okay, so we'll first understand what we're going to study in this chapter. Okay, so this chapter is about the effect of current. We'll study about magnetism but as a effect of current. Okay, till now we have studied about charges at rest in the first two chapters, and then current electricity in the third chapter. Current electricity, charges were in motion, and this moving charges, they create effects like heating effect we study. They also create magnetic effect too. Okay, and as a we'll study in this chapter magnetism as a fact of this moving charges or current. Okay, so let's begin then. Explain the important lines to you. Read the whole line and explain the important lines to you. Okay, so now so both electricity and magnetism have been known for more than 2000 years. However, it was only 200 years ago in 1820 that it was realized that they were intimately related. Okay, so they have a relation. Electricity and magnetism have a relation. It was found out after a long time. During a lecture at Demons in the summer of 1820, the Danish physicist Hans Christian noticed that a current in a straight wire caused a noticeable deflection in a nearby magnetic compass. Okay, so when Oyster was doing an experiment with a straight wire, what he noticed when he placed the current carrying a compass near a conductor which was carrying current, a conductor was there and it was carrying current. He must have connected it to some battery or other AC source, and what he said that when he placed a compass, accidentally he placed a magnetic compass near it. Okay, and there was a when he switched on the current, what he noticed that there was a deflection in this compass. Okay, now he questioned like what caused this magnetic compass to move. We know if we bring a magnet near a magnetic compass, then there will be deflection in the magnetic compass. Okay, and so it is because a magnet will create force on this magnet. Other magnet, they have magnetic field. Okay, we'll study it about later in the fifth chapter. Okay, so only a magnet can influence another magnet. So magnetic compass, you must have played with magnet, and two magnet, they exert force on each other. North pole, opposite pole attract, and um, like pole repel. But here there is no magnet. So how is this magnet created? How is the this magnet compass has been deflected? So he he gave a hypothesis that the current is producing a magnetic field. That's what's causing this magnetic compass to show deflection. Okay, and here the journey of magnetism, the relation between magnetism and electricity was established first. He investigated the phenomena. He found that the alignment of the needle is tangential to an imaginary circle, which has the straight wire as a center and is plane to the wire. Okay, so now, and it's all about the direction. How the direction was there? Okay, the direction of it was like perpendicular to this compass. Okay, this situation depicted in figure, you can see the figure here, how the magnetic field is there. Okay, like this. Okay, magnetic compass was deflecting, like showing deflection like this. Okay. Mm. We'll understand the direction in all this in later paragraphs. Okay. Now, reversing the direction of the current reverses the orientation of the needle. And when we reverse the direction, what is said, find out that direction of the orientation of the needle also changes. That is, if a deflection was like this, north south here, if it create the current, then the deflection was opposite. The south was earlier, north was here, south was here. So changing the direction of the current changes the orientation of the needle. The deflection increases on increasing the current on bringing the needle closer to the wire. Okay, as and when you bring the needle closer to the current carrying wire, what he noticed that the deflection will increase, suggesting that the magnetic field is stronger near the conductor, okay, or decreases as we go away from the conductor. Iron filings sprinkle around the wire arrange themselves in concentric circle with the wire at the center. Also concluded that moving charges or current produce the magnetic field in the surrounding space. Okay, and when he did another experiment, and you must have done it. Okay, so if we sprinkle iron filings around a magnet, what we notice, there's a pattern. There's a pattern in which this iron filings arrange themselves. Okay, they arrange themselves like this. Some pattern is there, and this pattern is similar to the pattern in which the magnetic compass was arranging themselves when we place it in the near the current getting wire. So what he was conclusion, this is the important line that we must understand. Moving charges are or currents produce the magnetic field in the surrounding space. Moving charges produce a magnetic field. This was the conclusion. Okay, now following this three, there was intense experimentation. In 1864, the laws surveyed by electricity and magnetism were unified and formulated by James Maxwell, who then realized that light was electromagnetic wave. It is very breakthrough thing, breakthrough kind of experiment. Okay, and that he, what he united, unification of electricity and magnetism. Like light was you will study is about in chapter 8, that electricity and magnetism. Light has both electric field and magnetic field, and these two were united. He gave the hypothesis in theory, and then and then Marconi and J.C. Bose and Hertz, they did it experimentally proved it. Okay, so all, and now we have this application of electromagnetism, like production, amplification, transmission, detection of electromagnetic wave, and it's really helpful. I mean, totally our modern amenities and modern devices are based on this. Okay, about phone or electromagnetism, you will study in electromagnetic wave chapter, then we'll see the application part there. uh, in this chapter we will study how magnetic field exert forces on moving charges like electron, proton, and current getting wires. Okay, so what we'll see that magnetic will exert force on charged particle, not charged particle, moving charged particle. This is important, you have to understand, not charged particle but moving charged particle, electrons, protons, any charged particle. Okay, and how currents produce magnetic field, understand that. And we also understand about some devices that cyclotron to accelerate charged particle with the help of magnetic field and electric field. And then we'll study how current and voltage are detected by galvanometer. Okay, so this is all we have to study in this chapter. Okay, now after this, in this subsequent chapter of magnetism, we adopt the following convention. One convention we have to follow, like if you see a symbol like this, a circle and a dot in it, it means that the field is out of the paper. The magnetic field coming out of the paper towards you. But if you see like the symbol like this means that the magnetic field is going into the paper. Okay, so that you have to remember. And now we are ready to start the next paragraph, and this is 4.2, magnetic force, sources and field. Before we introduce the concept of a magnetic field, capital B, we represent magnetic field by with a symbol capital B. Okay, and it's a vector. We shall recapitulate what we have learned in chapter 1 about the electric field. Okay, we just recall what we have studied about electric field and we'll relate it to now magnetic field. We have seen that interaction between two charges can be considered in two stages. The charge Q, so source of the field, produces electric field E. We have understand the concept of field there. What a charge do? What a charge do? As according to Faraday, it doesn't just act force on the other charges. It creates its own field, and when another charge comes in the vicinity of the field, it experiences a force. Okay, Similarly here, and that field is, for a point charge, it is given by q. This is the charge, so source charge. Q, r cap, this is direction in unit vector direction, and q upon 4 by epsilon naught r square is the distance between the point where we are considering the field, the and this q, this epsilon naught is the permittivity of the free space. We have already discussed in the first chapter. Now all these parameters are given here, explained here. Now another if a charge of magnitude small q comes in this field, it will experience, it will experience a force. And how much is the force? It is a charge times the electric field, and we can put the values here, and we will get an expression for force. As pointed out in the chapter 1, the electric field is not just an artifact but as a physical role. It can convey energy and momentum, and is not stabilized instantly but takes finite time to propagate. Okay, so it had the field has energy as well as momentum, and it is not instantaneous. Okay, it will create some time. The field, the forces will not act instantly. First the field will be created, it will take some time. Okay, and then it will act force on the other object, on the charge. The concept of field was specially stressed by Faraday and was incorporated by Maxwell in his unification of electricity and magnetism. So first Faraday had stressed about it, and then Maxwell had unified, given it in his unification theory. In addition to depending on each point in space, it can also vary with time, be a function of time. Okay, those it will vary with space, obviously. Different region, the electric will be different, and also with time it will vary. Okay, so now in chapter we will assume that field do not change with time, but in this chapter what we'll study, that it doesn't vary with time. Time varying magnetic will study in the later chapter. The field at a particular point can be due to one or more charges. Okay, and the field will be due to, that can be one charge and more than one charge. We already studied in the, and that will apply the superposition principle. Okay, that sum of the electric field will be the sum of the individual electric field vector, sum of the individual electric field. Just as static charges produce an electric field, the current or moving charges produce magnetic field. Okay, they also produce magnetic field given by Br. Magnetic field is a function of R, the position vector. Different, it will vary with position or distance. Again, a vector field. It has several basic properties identical to electric field. Okay, like it is defined at each point, like electric field is defined at each point. It does also, it depends on time also, time varying magnetic field. Okay, principle of super, it also obeys the total magnetic field will be the sum of the magnetic field due to individual charges, moving charges. Okay, so now this was a 2 paragraph explained. Now the remaining paragraph I will explain in the new video. Thanks for watching.